Alright, today we're going to talk about Chapter 5. Chapter 5 is going to focus on work and power. So let's talk about what is work. Okay, so before we go any further, you guys can decide in your groups a little bit, what do you think work is? You can pause and go through that. Here's what we know. Many people think the word work means that you have to do something to earn money. Not always true. The word work also means you exert a force with your muscles, such as when you're writing or typing. Sometimes you might say that you have to do work when you push as hard as you can against the wall, but it doesn't move. So, work makes something move. That's a big thing that we need to make sure that we focus on here. If it doesn't move, did you really do work? I don't think so. And that's a misconception that we have. So let's talk about that a little bit. However, in science class, the word is defined a little bit differently. So remember that a force is a push or pull on an object. In order for work to be done, the force must make something move. So you must have an unbalanced force, not a balanced force. If two people are pushing in opposite directions with the same amount of force on an object and the object does not move, work is not being done. Because work is a transfer of energy that occurs when the force of the object moves. So you have to make the object go from potential energy to kinetic energy. If you don't have that motion, no work is being done. Even though you're exerting energy, however, you haven't done any work yet. So you can hold the stack of books in your hand for hours and hours on end. But unless you walk with them or move them, you haven't done any work. So when you're doing work. So, if you push against a desk and nothing moves, you haven't done any work. If there are only two conditions in which you have to be satisfied in order for work to be done on an object, one, you have to apply a force that makes the object move. Big deal. It makes the object move. The object doesn't move, you don't do work. The other is the movement must be in the same direction as the applied force. It can't be in the opposite direction. It has to actually be in the applied direction of that force. Okay, so here's an example. The lady right here is lifting with her legs a stack of books, and she's having an upward force. She's pulling the books upward towards herself. The force and the distance that the books are moving are in the same direction. So the lady is doing work on those books because her arms have done work because the books have actually moved. And so she's meeting both stipulations here in this case. So when you carry the books while walking, you might think that your arms are doing work. However, in this case, the force exerted by your arms does not do work on the books. If you think about this, your arms are holding the books parallel or to your chest, but they're not moving. You're not moving the books in those same directions. The force exerted by your arms on the books is an upward or horizontal motion, and the force exerted is in the right angle to the direction the books are moving, like this right here. So you're pulling upwards on that force, but your feet are moving forwards. So therefore, you're not doing work on the books. Okay, work is not done. Transfer of energy is always occurring. Remember, you don't have to have work done to have a transfer of energy. That's a little bit of a misconception that we have in physical science, is that, oh, I transferred energy, I must have done work. Well, not really. Energy is being transferred all the time in our environment. We just don't always see it. This is an easy way to understand, if you think about it, how you feel when you're carrying a heavy box up a flight of stairs. You're transferring energy from the moving muscles into the box and increasing its potential energy as you increase its height. You may recall that energy is the ability to change. Another way to think about energy is that energy is the ability to do work. If someone or something has energy, it can transfer energy to another object by doing work on that object. So when you're lifting those heavy books from the floor up, you're actually doing work. When work is done on an object, you increase its energy. Now, you might be changing its potential energy into kinetic energy. So if that student is carrying a box and transfers its chemical energy from its muscles to the box is now moving and has kinetic energy. The energy is always transferred from one object that is doing the work to the object that the work is being done on. You will also see that some objects will transfer, you'll have some extra transfer, and that's for thermal energy. So how do we calculate work? So the amount of work being done depends on the amount of force exerted on the distance applied, over the distance applied for that force. So when force is exerted and an object moves in the direction the force was exerted in, the amount of work being done is calculated by work is equal to force times distance. Again, you can write that equation onto your equation sheets. So there it is. Work is equal to force times distance. Work is always measured in joules. Oh, that looks like a familiar thing. Kinetic energy, potential energy, work is transferring energy. Oh yeah, it's still joules. And then we have force, which is in newtons, that has not changed, and distance, which is in meters. Remember, if they give you a distance in kilometers, you must convert that to meters first. And in order for work to be done, you have to have the force moving the object in the distance or direction the force is being applied. Okay, in this equation, force is measured in newtons, distance always in meters, work will always be measured in joules. 1 joule is about the same amount of work required to lift a baseball vertically, 0.7 meters, or 70 centimeters. So not that far. So suppose that you give a book a push and it slides along a table for a distance of 1 meter before it comes to a stop. Even though the book moved 1 meter, you do work on the book only while your hand is in contact with it. Once your hand removes from the book, you are no longer applying a force, and so you are no longer doing work on that book. So let's talk about power, because power and work kind of go together. Oh, okay, so suppose that there's another student pushing the box of books up a ramp and he loads them into a truck. To make the job more fun, you make a game out of it and you race to see who can push the box up the ramp the fastest. So, here's an example of a girl pushing a chair up this ramp into a moving truck. Power is the amount of work being done in 1 second. So it's talking about the rate at which it is being done. So it's just taking 1 second of time. So you have to know that there's work being done in order for power to be measured, because it's just calculating that rate. So power is calculated, divided the work by the time required to do the work. So again, the SI unit for power is watts, or W. 1 watt is equal to a joule, and work is being done in 1 second. We'll typically see power measured at our homes in kilowatts, mainly because we have so much going in at one time. Okay, so power is equal to work divided by time. Again, it's the rate at which work is being done, and it's the measure of the watts. So, just as power is a rate at which work is being done, power is also a rate at which energy is being transferred. So if you think about this, when we have electricity coming to our homes, we are transferring that in. That's why we see it measured in kilowatts. And when energy is transferred, the power involved can be calculated by dividing the energy transferred by the time needed for the transfer to occur. This is also why they have a meter outside of your home measuring how much energy is coming into your home at a given time. And unless you have an immense, like Bill Nye the Science Guy, and has solar power for something, or wind energy to power your house, you're going to see that moving constantly. If you have energy coming into your home, you'll see, if you go out and look at your meter is always moving in one direction. If you go to Bill Nye's house, it's moving in the opposite direction. He has solar power to help power, so he actually makes more energy than what he's pulling from the electrical plant, so he is actually putting energy back into the grid. But you can go out and look at your house and see the energy transferred. Let's work on some problems really quick. So you guys can get whiteboards if you want, and let's work through these. So there's a force of 40 newtons to pick up her child, a distance of 2.8 meters. How much work is being done on her child? Okay, so what are we given? We're looking for work. We're given force, and she moved it in a distance of 2.8 meters. So she did actually move her child in the same distance the force was applied. So why don't we pause the video and calculate for work? So work is using the equation force is equal to force times distance is equal to work. So you took 40 times 2.8 meters and you got 112 joules. Remember, it's still energy, it's joules. So let's do another problem. Matt uses the force of 1,525 newtons to drive his car a distance of 381 meters. How much work is being done on his car? Okay, well, let's see what we were given. We were given newtons, so that means we were given force of 1,525 newtons. We were given a distance of 381 meters. His car went in the same direction as the force, so work was being done. So we can calculate work. Go ahead, you can pause the video, and you can calculate work on your whiteboards. Okay, so you should have used the equation. Work is equal to force times distance. You took 1,525 times 381, and you saw work being done at 581,025 joules, or 581,025 joules. Let's do another one. So Mary uses 27 joules of work to carry a load of laundry that she has done with a force of 17 newtons. What is the distance that he carried the laundry basket? Well, you're given work this time of 27 joules. You have a force applied to that laundry basket of 17 newtons, and you need to know the distance that it was traveled. You can go ahead and pause the video and try to solve this on your own. You should have used distance is equal to work divided by force. So distance is equal to 27 joules divided by 17 newtons, and you would get a distance of 1.59 meters. Again, in meters, not kilometers. If it's there, you have to convert it. So let's do a couple power problems now. So a figure skater lifts her partner who weighs 450 newtons, a distance of 1.5 meters in 30 seconds. How much power is being done? Well, they didn't give us work. So what did they give us? They gave us force, which is 450 newtons. They gave us a distance of 1.5 meters, and they gave us a time of 3 seconds. And they want us to find our power. So why don't you go ahead and you solve for that. Power is equal to work divided by time. So you had to find work first. So you took your 450 joules times 1.5 meters to get 675 joules. Once you have your 675, you would find out that you need 675 divided by 3 seconds, and that would give you your answer of 225 watts. Note, they can give you all the information that you can solve work for, and then you can find your power. Don't forget. So, now that we've gone through those, I hope you guys have a great day, and you have a worksheet and an assignment on Classroom.